Well, I hope everybody, all the 20, 30 of you, however many there were, had AP tests yesterday. Hope that went well. We're back at it with our Brownie stoichiometry packet that we started on the 11th. And we're on page 2 here. And now we're going to do some real chemistry, not brownies. I hope you guys, some of you made those brownies. Let me know how they turned out. Send me a picture. So this first part is going to be with a very important equation that you'll see lots and lots in chemistry classes. It's the equation where we take nitrogen and hydrogen and make ammonia. You can get all fancy and call it nitrogen trihydride, but making that ammonia was worked on for years by many scientists. The process we use now is something called the Haber process. Fritz Haber was a German chemist who's really not a nice guy. At any rate, it takes tremendous amount of pressure and tremendous amount of heat. And of course, back in the early 1900s, how did you get heat? You got it with fire, and of course having hydrogen around fire, is not a good idea. At any rate, it was a big deal when someone managed to do that. Of course, Haber was doing it so the Germans could make explosives, TNT, trinitrotoluene, and dynamite. Both need ammonium nitrate, and H4 is now NO3 is now used as fertilizer, and so an original process that was developed to kill people is now keeping people alive via agriculture. Kind of ironic. Anyway, little aside. So this equation is the equation. Remember, nitrogen and hydrogen are diatomic gases. Ammonia is also a gas. The stuff that we buy at the store that's called ammonia is actually ammonium hydroxide. It's ammonia gas that's been percolated through water, which creates ammonium hydroxide. But at any rate, this is not balanced, right? We've got 2 hydrogens here and 3 here, 2 nitrogens here, 1 here. Right off the bat, we know that this nitrogen molecule is going to come apart. We saw this in the PowerPoint, if you watched that. It's also in your textbook. So I know I need these 2 nitrogens to separate. And then for hydrogen, now we have 2 on this side of the arrow, and 2 times 3 are 6. So we're going to do the 3-2 switcheroo, if you will, and put a 3 here. And again, we don't have anything in front of nitrogen, but if it makes you feel better, you can write in a 1. So the ratio is 1 of these combined with 3 of these will make 2 of these. Okay? So again, we're going to start with easy examples. You can probably see this right off the bat. 7 moles of nitrogen gas. How many moles of hydrogen would you need to go with it? Right? Kind of like, you got 8 eggs. How many batches could you make? You got 8 eggs. How much margarine do you need to go with it? Same idea. So again, we always start with what we're given, get some sort of a ratio, and then we're left with our asked for. So 7 moles of nitrogen. What's the proportion from my recipe? The stuff that they're asking for is hydrogen, so we need that on top. Stuff that we're given is nitrogen, that goes on the bottom. And from my recipe, 3 of these go with 1 of these. When we do our little quick process, and of course this is understood to be moles, okay? Moles of nitrogen, cancel moles of nitrogen. We're left with moles of hydrogen. And probably you figured this out a long time ago. That means you're going to need 21 moles of hydrogen. Okay, so we're 7 timesing our recipe, right? 7 times 1 is 7, 7 times 3 is 21. You can probably figure out where we're going from here. So the next question, starting with the same amount of reactant. Remember, this is understood to be over 1, just to make our little math solution possible. What are we trying to figure out? Ammonia. What are we given? Nitrogen. From our balanced equation, 2 of these for every 1 of those. So twice as many molecules of ammonia are going to form as molecules of nitrogen that we had to start with. And then the next question, hopefully you can solve pretty easily. If I had 21 moles of hydrogen, of course we already solved for this. The question is, would your answer be the same? How many moles of ammonia would you get from that much hydrogen? Again, just following the process, 2 of these for every 3 of these. The moles of hydrogen cancel. 21 times 2 is 42 divided by 3. Isn't that easy for me to do, but probably most of you can see that, yes, they're the same. All right, hopefully that makes sense. Now, we're not actually counting atoms and molecules or moles of them. We're actually needing to do molar mass. We actually measure things out on the balance and go from there. So it's a little more involved. This is where that multiple step thing comes in. Whatever number of grams you have to start with, you got to change it to moles. You need the mole ratio from the balanced equation to get the moles of the asked for substance, and then multiply by the molar mass to get the number of grams of the asked for substance. So let's see how that goes. Okay, and you can read through the top here. It's the same equation, so let's put our same coefficients in. Mole ratio is 1 of these, goes with 3 of these to make 2 of those. Molar mass of nitrogen, we'll just go to whole numbers just to make it easy on ourselves. So nitrogen's 14, so 2 times 14. When you look at the periodic table, that means nitrogen gas is 28 grams per mole. Hydrogen gas is 1.01, we'll just go with 1. So 1 and 1 and 1 means a mole of a mole of hydrogen gas is 2.0. And again, nitrogen's 14, hydrogen's 1, hydrogen's 1, hydrogen's 1, 3 times 1. So a mole of hydrogen of ammonia gas is going to be 17 grams per mole. All right, so the next thing that I wanted to show you is how the fact that the total number of atoms and the number of grams are the only 2 things that stay constant in a chemical reaction. We can have different numbers of molecules at the beginning and at the end. We can have different volumes of gas, all that kind of stuff. So when we look at the coefficient, 1 nitrogen, so 1 times 28, 28 grams, plus 3 times 2 is 6 grams, hopefully equals 2 times 17. And obviously it does. Okay, mass at the beginning equals mass at the end. Atoms at the beginning are all present at the end. They just rearrange. So here's what we're starting with. 19.6 grams of nitrogen gas. How many moles of hydrogen gas? So we're actually only going to have to go to here, are present. So first thing we got to do is change grams into moles. So I need moles on top, grams on the bottom. We know 1 mole of nitrogen gas is 28 grams. We could stop there and get an answer, or we can keep going. So I'm not interested in moles of nitrogen, I want to know moles of hydrogen. So for my balanced equation, 3 hydrogens for every 1 nitrogen. So here's what you can do, and maybe some of you can see this right off the bat. Everything in the numerator gets multiplied together, divided by everything in the denominator multiplied together. So 19.6, excuse me, times 1, which really isn't necessary, times 3 equals this, divided by, and this is important for when you have something other than a 1 here, 28 times 1. Now I didn't have to do that, but I wanted to show you, okay? And that ended up being 2.1 moles of hydrogen. Okay. I'm going to ask you to do number 6, and I'm going to ask you to do number 7 following this process, okay? It's the same process. I think you'll be able to do just fine. The next part of this assignment is writing the balanced equation that's written here in number 8, magnesium and aluminum sulfate. And so you know magnesium's Mg, you know aluminum's Al, you know sulfate is SO4. You have to remember that magnesium ends a +2 charge when it goes into a compound, aluminum's a +3, and sulfate's a -2. Remember, compounds don't have charges. That's just to help you in making the formula. So what I'd like you to do for tomorrow is just complete this equation and this data table, okay? Don't need to do the problems yet, okay? Please don't do the problems, just get ready for this last, what page am I on? Do number 6 and number 7 and this equation data box. That's all I want you to do, all right? Have a good one, talk to you tomorrow.